Okay, here we are back on again. Okay, so the first thing I talked about yesterday was about moments of random variable. I mean, we talked about it in the beginning of this course. That is, if you have a random variable x, then the mean is the expectation. The variance is given by this formula here. But there are higher moments. There are higher moments than mean and variance. One of them is called the skewness, and it's defined by this formula. And another one is called kurtosis, which is defined. The kurtosis is defined by this formula here, right? Okay, guys. So the skewness measures whether the data is skewed to the left or the skewed to the right. So it can take positive or negative values depending on whether it's positively skewed or negatively skewed. And the kurtosis is a measure of peakedness of X. So the larger the value of kurtosis, the more peaked the distribution is. All right. And another thing is the nth moment, which I talked about in this course too. So for example, when n is 1, you get the mean. When n is 2, you can use it for the variance. When n is 3, you can use it for the skewness, and so on. So yesterday I did one example. Sorry, this is the first example I did. And where I computed the nth moment and the mean and the variance. I also did another example. This is the second one, where I computed the nth moment and the mean and the variance. Then I did a third example. This is a discrete example where I computed the nth moment and the mean and the variance. Okay, and then I talked about generating functions. And this is something you will learn about in probability 2. By the way, the class is tomorrow. Tomorrow we have 2 classes from 11 to noon and 1 to 2 p.m. In the 2 classes, I will talk about statistical methods. Because statistical methods is a course you will take in semester 2 of next year. And I will talk about what things you will learn and which follow up from what you have learned in this course. So the things that will come up following up from what we have learned. Okay, so please, if you have time, please try to come to the 2 classes tomorrow, 11 to noon and 1 to 2 p.m. Okay, all right. Generating functions. So if you have a variable x, there are 3 common generating functions. The first one is called the moment generating function. Is defined as the expectation of e power tx, right? It can be used to derive the moments, as I have shown here. The second one is called the probability generating function, or PGF, and is defined by g of t equal to expectation of t power x. And the reason it's called PGF is because it can be used to derive the probabilities, right? And the third one is known as a characteristic function. Okay, and it's defined by this here, where I is the complex number. The thing about the characteristic function is that it uniquely determines the distribution corresponding to it. So for every distribution, there is only one characteristic function, and for every characteristic function, there is only one corresponding distribution. So there's a unique correspondence, and also the characteristic function exists. It exists for every distribution, meaning that, I mean, the Mgf may not exist or the PGF may not exist, but the characteristic function does exist for every given variable x, right? So that's is a powerful tool. I mean, I will talk about some of the applications of these 3 different functionals later on today. All right. Now, then I did excuse me. Then I did one example where I derived the Mgf. This is the derivation for the Mgf. I derived the Pgf, which is this one, right? And I also derived the characteristic function, which is this one. Okay. That's example one. Example two, I considered the uniform distribution from 0 to A, and I derived the Mgf, which is given by this, the Pgf given by this, and then I also derived the characteristic function, which is given by this. Okay, guys. So it's a summary of what we did, which you were not here yesterday. This is a summary of what I did yesterday. Right? Okay, guys. Any questions on what we did yesterday, or before I go ahead? Okay. All right. So let me close this one and start a new page. So let me close and let me excuse me. Okay, just a minute. Give me a second, guys. Okay, guys. All right. So what I'm gonna start doing today is try to do more examples. So I will start with example 3, right? Example 3 is suppose you have a normal variable and we want to derive the 3 functionals. So first of all, the Mgf. Okay, so the Mgf is m of t, which is defined as the expectation of okay, so this, remember, this is the, what I have written here is the PDF of the normal distribution. I'm sure all of you know this, right? This is what I have written here is the PDF. Now, okay, computing this integral is something of a task. So let me try to do it slowly. If you have questions, try to use the chat box, okay? If you're just joining us, we just started doing an example with where variable has normal distribution, and I'm trying to derive the Mgf. Mgf is something I talked about yesterday, right? So This is what you get. Now, you can take the common factor 2 sigma squared. Okay, before we do that, let me do this. Let me try to expand this term here. So you get minus no, I shouldn't do this. Sorry. Let me erase this, guys. Sorry, I made a stupid thing. I shouldn't do this. Sorry. Okay, excuse me, guys. Okay, what I meant to say is, let's take a common factor of 2 sigma squared, right? 2 sigma squared in the denominator. So if you take this common factor, then in the numerator you will have this 2 sigma squared tx minus okay, this is what you get. Okay, and this will be this. Okay, if you're not following me, just talk to me. Okay, don't be shy. Okay, now this will be okay. I'm gonna expand x minus mu squared, so you get 3 terms. You get 3 terms, right? Like this. Okay. Now I'm gonna do something you may be familiar with. If you're not, I will let you know what it is. Do you know something called completion of squares, guys? You probably learned this long time ago, but maybe forgot. Anyway, let me try to show you what I'm trying to do. Is x squared. I'm gonna group the x terms together. So it's gonna be minus 2 mu minus sigma squared t x. Oh, sorry, is it minus or plus? Just a minute. No, it should be plus. Sorry, plus. Yeah, then plus mu squared divided by 2 sigma squared dx. All right. Are you with me, guys, so far? Don't be shy to ask questions, okay? All right. Now, the next step is what is known as. In the next step, I'm going to do what is known as completion of squares. You should know this. If you don't know, just watch what I'm doing. All right. Now, the first 2 terms, that is x squared minus 2 times something x, can be put together into this, right? Okay, and then because you're introducing an additional term, right? Because you're introducing an additional term, which is the third term, you need to subtract that. Plus mu squared. Do you follow what I'm saying? This, I mean, this trick, okay, this trick is known as let me use this step here is known as the completion of it's known as the completion of squares. I think you probably know this. I mean, if you don't know this, just you should have learned this in your first year, well, in semester 1 or something like that. Okay, okay. Now what I'm going to do now is I'm going to take the last two terms outside the integral because they are constants, right? So it's going to be, excuse me. So these are the last two terms inside the integral. I've taken them outside. Now, what is left is the following. 1 divided by, okay, and this multiplied by the integral e okay. So this is what you have. Now, let me ask you, what do you know about this? This thing here, I mean, the thing I have highlighted in red is what? Is the integral of a density, namely the integral of a normal density, right? So let me write it down. This what I have written here is the integral of the PDF of a normal density with parameters, with the mean parameter equal to this and the variance parameter equal to this, right? Right. And you know that from probability 1, which you did last semester, that the integral of a PDF must be equal to 1, right? So this must be equal to 1, right? Right. So therefore, the answer is this is the whole thing is equal to 1. So what you have is E okay. Now you can simplify this further to, if you expand the first term, you will get 3 terms. One of them will cancel with this. So the remaining terms will be 2 mu sigma squared t plus sigma power 4 t squared in brackets divided by 2 sigma squared. So this is gonna be equal to E mu t plus sigma squared t squared equal to 2. So after a lot of calculations, I mean, it looks like a lot, but you will get used to it when you go to probability 2. So what we have shown, is the MGF, of a normal variable is equal to E right. So let me put this in a box. So this is, we have shown that the MGF of a normal variable is given by this expression. Okay. Any questions, guys, or no? You guys okay with that, or you have any questions, guys? All right, so that's example 3. Now, similarly, you can find the PGF. I'm not going to do it, but you can show you can show that the PGF of a normal, which is denoted by G of t, is equal to E mu log of t. I'm not going to prove it, but I will leave that as an exercise for you. This is the PGF of a normal variable, and you can also show that the characteristic function of a normal variable is E mu it, where I is the complex number, minus sigma squared t squared divided by 2. All right, once again, I'm not going to prove it. I will leave that as an exercise for you to do. So that's example 3. I will do one more example, and then I will talk about the important application of MGFs, right? So the next is example 4. Suppose you have a variable x that has a chi-square distribution with parameter a. I mean, this is a distribution we talked about before the Easter break, you may recall, right? Chi-square distribution. Right now let's suppose we want to find the MGF. The MGF so this multiplied by the density of the chi-square. You may recall from much earlier on in our course that the density of a chi-square distribution is given by this formula. Okay, this is the density of a chi-square, right? I hope you recall this from what we did a long time ago in our course. All right, so you can pull the constants outside the integral, so this will become this. Then you have the integral from 0 to infinity of x power a over 2 minus 1. Then e in brackets, you're going to have x of half minus t dx. Okay. Now to work out this integral, I'm going to use the definition of a gamma function, which I did yesterday also, because remember I did that yesterday. So I'm going to make a substitution first of all. So I'm going to make set y equal to x times half minus t. Okay. So x will become y divided by half minus t. Okay. So dx is equal to dy divided by half minus t. Okay. You follow me? Okay. Now I'm going to make this substitution into the integral. All right. So let's see what we get. So you get 1 . So x will become y divided by and dx will become dy divided by half minus t. Okay. Okay, guys, are you okay? So now I'm going to pull out the constants outside the integral. So this is going to be 1 divided by you guys okay? Welcome, guys. You're just joining us, welcome. This is what you get, okay? Now you may recall from yesterday that this integral here is simply the gamma function. It's the gamma function at a by 2. So all right, this integral here is simply the gamma function at a over 2. All right, so this guy here and this guy here, they cancel out. So what you get is the following. What you get is 1 divided by 1 minus 2 times t power a over 2. So just to summarize, guys, what we have shown is the Mgf of a chi-squared variable with a degree of freedom is equal to 1 minus 2t power minus a over 2. All right. And similarly, you can show that the PGF, I'm not going to prove it, but I will leave that for you to prove that the PGF of a chi-squared variable with a degree of freedom is equal to this. And you can also show that the characteristic function for the chi-squared variable with a degree of freedom is this equal to this. All right. So again, you can try to prove it by yourself. I mean, okay. So these are the main results for the chi-squared variable with a degree of freedom. And okay, guys. All right. So the next thing I'm going to talk about, maybe I can. Well, I would. Yeah. The next. I mean, we are done. For example, I guess that's enough. But the next thing I'm going to talk about is how we can actually use. I mean, what is the use of the all these results that we have derived, like the MGF and the PGF and the characteristic function. Okay, so it's kind of application. What is the application of what is the application of MGFs? That's what I'm going to talk about now, because I mean it's fine having all these results for different random variables, but what do they use? I mean, what can you use? What practical use they have, or they're going to have? All right, so I'm going to talk about one or two of them today. Right, the first one, you may recall, I think this is a result I mentioned in the class long time ago. When I talked about the normal distribution, this is a result I mentioned. Then the linear combination of the two random variables will have the following distribution: a normal distribution with parameters. Excuse me. This is, I'm sure, I did mention this result. I don't know, some of you may recall this, I don't know. This is, what this result says is that, it says that you should have two independent normal random variables, then their linear combination, where alpha, beta, gamma are constants, also has a normal distribution. Okay, now this result, I said that you don't need to know the proof of this result for my course, but when you go to probability 2 next year in semester 1, you will need to know how to prove this for probability 2. Now I'm going to show you how to actually prove it using the stuff we learned, right? Now, okay, so here's the proof. So you have an advantage of knowing the proof for probability 2, right? Okay. The proof goes like this. Let Z or Z denote alpha X plus beta Y plus gamma, right? Then the moment generating function of Z is as follows: is M of t equal to the expectation of E t z, right? Which is equal to the expectation of E t like this, okay? Now this you can write as the expectation of T alpha x, expectation of T beta y, and the expectation of T gamma, okay? Now because x and y are independent random variables, so here I'm using independence of x and y. Okay, so in this step, in this step, let me write down in color. I'm using independence of x and y, right? Because x and y are independent variables, you can say that. Okay. Okay. Now we know that this guy here, the first term, is the Mgf of x. So we can use the result that we already know from example 3. Right, in example 3, we derived the Mgf of x, right, which is let me, I don't know whether you, okay, maybe some of you came late. Just a second. Here we are. Some of you came late, so let me show you, for those of you who came late, let me show you example 3. If you look at this is example 3, and I showed example 3 that the Mgf of a normal variable is mu t plus E mu t plus sigma squared t squared divided by 2, right? Now I'm going to use that result over here. Right? So the expectation of E t alpha x is going to be A t alpha, right, plus sigma squared, which is b squared t squared alpha squared divided by 2. So that's the first thing, right? And similarly, the second term, which is the expectation of E t beta y, is b t beta plus d squared t squared beta squared divided by 2, right? And finally, you have the third term, which is E of t gamma, right? Now, combining these three terms, I'm going to combine the three E terms because remember the product of exponential is the exponential of the sum. So you can write this as A alpha plus B beta plus gamma times t, right? Then plus B squared alpha squared plus d squared beta squared times t squared divided by 2, right? Now what you have here, guys, all right, if you look closely, this is precisely of the form, what you have is precisely of this form, okay? Okay, it's of the form mu t plus sigma squared t squared divided by 2, where, excuse me, where your mu is the mean parameter, is equal to A alpha plus B beta plus gamma. And your sigma squared parameter, the variance is b squared alpha squared plus d squared beta squared, right? So hence, Z, okay, Z must have a normal distribution with parameters A alpha plus B beta plus gamma. That's the mean parameter. The variance B squared alpha squared D squared beta squared. So this is the proof. The proof is complete. The proof. Do you follow what I've done? Let me take you through this if you did not. Okay. So what I did is to call Z alpha x plus beta y plus gamma, and then I started deriving the MGF of Z, which you can write in this form. That is, using independence of x and y, you can write the MGF of Z in this form. And this using example 3, right, which gives you the MGF of a normal variable, right? You can write down the expectation of E T alpha x as this, and the expectation of E T beta y as this. Now, simplifying, you get to something of this form, which is precisely the MGF of a normal variable with parameters mu being equal to alpha plus beta, b beta plus gamma, and sigma squared equal to b squared alpha squared plus d squared beta squared. So hence what we have shown is that the MGF of Z, which is the linear combination of x and y, is equal to the MGF of a normal variable with mu and sigma squared. So hence Z must have a normal distribution. So that's the logic. I don't know whether you follow what I said. The logic is to show that the MGF of the linear combination is the same as the MGF of a normal variable, right? If you can show that, then it follows that linear combination, which we called Z here, must have a normal distribution, right? So this is the proof of this property, which I mentioned in our course, Intro to Statistics. I mentioned this property a long time ago without proving it, but you will need to know the proof of this in probability 2. I mean, you will learn the proof of this in probability 2. So it's good that you already know this if you can follow what I've done, right? Are you guys okay or not? Any questions? All right, another so that's one application. Sorry, excuse me. That's one application. If you have questions, please use the chat box, guys. If you have questions, please. The second application I like to talk about if I have time. I don't know if I will or not, but the second application of MGF is the following. Suppose suppose you have IID normal variables, right? Okay, then X bar, remember X bar is the sample mean. Also has a normal distribution with parameters mu and variance sigma squared by n. Now this result, I also mentioned this result in our course intro to statistics. But again, I did not give a proof because it's not needed. But in probability 2, you will know how to prove this. So let me give it to you now already, so you will know it in advance, right? All right. The first thing you must do is to find the MG. So the idea is to find the MGF of X bar and show that's the same as the MGF of a normal variable with parameters mu and sigma squared n. Okay, so the MGF of X bar is gonna be MT, is the expectation of ET X bar, right? Which you can write as the expectation of ET X bar is 1 over n times okay, like this. Okay, now let me write this in a more simpler way. So it's gonna be T over n x1 up to T over n xn. Okay. Now because x1 to xn are independent variables, you can write this like this. Just using right. That's using using independence. Okay. Now what you have here is the MGF of x1 with t replaced by t by n. So you can write this as E of mu t replaced by tn, right? Sigma squared with t replaced by tn. This is it's using the result of example 3, right? Okay, you follow what I'm doing, right? This I'm using the example 3, the result of example 3, which we did earlier today, right? Okay, so this is gonna be let me write this in a slightly different way. Mu tn plus sigma squared t squared divided by 2 n squared. Okay, mu t divided by n plus sigma squared t squared 2 n squared. Right. Now you have n of these terms. So when you take the product of n of these terms, this is a bit like to the power n. So what you're doing is you're raising this to the power n. Okay. So you get mu t plus sigma squared t squared divided by 2n. Now what you have here is the MGF of, okay, what you have here is this is precisely what you have here is the MGF, the moment generating function of a normal variable with parameters mu and sigma squared over n. Okay, so hence we have shown that x bar, the sample mean, must have a normal distribution with parameters this. All right, so the proof is complete. So you see the logic is the same as in the previous application. The idea is to excuse me. Let me, excuse me, sorry, what am I doing? The idea is to start with the MGF of X bar, right? And show that it's the same as the MGF of a normal variable. And that's what I have done here, right? So I have started with MGF of X bar and show that is equal to this, which is the MGF of a normal variable with parameters mu and variance sigma squared by n. Hence, X bar must have this distribution. That is normal distribution with parameter mu and variance sigma squared by n. All right, guys, any questions? So this is the second application of I wanted to talk about today. So the proof is complete once again. The proof okay. Are you okay, guys? So I think we are done. The time is up. Unless you have, do you have any questions, guys? You want me to go over? Hello, guys. Are you there? Are you okay, guys?
Yeah, well, okay, sir.
You have any questions you want to ask me before I?
No, sir.
All right, guys. So I'll see you tomorrow. Tomorrow we have two classes, one from 11 to noon and then from 1 to 2 p.m. Okay. So take care. So I'll see you guys tomorrow. And take care of yourself wherever you are.
Yeah, thank you so much, sir.
My pleasure.
No, thank you. Have a nice day, sir.
You too, guys. Have a nice day.
Bye. See you, sir.
See you.
Yeah.